Welcome to this edition of Engineering Track. Have you ever wondered how an aeroplane flies or how it navigates? Today we will educate you on the facts behind how an aeroplane flies. Recently, there were issues of collapsed building. We have a chat with a structural engineer who explained how to avoid it. Watch out for this and more on the show today. But first, engineering news. This is Engineering Track, and I am Temitayo Fagboro.
I don't know.
I don't.
Aeroplane used to fly through the air.
Over the last few decades, aeroplanes have revolutionized the way we travel. But have you ever thought of how it flies? How does it navigate? We will get answers to these questions in a simple but scientific way. First, let's look at some history. Many crazy flying machines are designed and tested in the 19th century because of mankind's quest to fly. Finally, one attempt succeeded. It was the flight of the Wright brothers. The aircraft was a success thanks to an interesting phenomenon of physics, the airflow technology. The wing of the aircraft was able to produce a lift force in an ingenious way. The wings had a curved shape. This shape pushes the gushing air downward. Newton's third law of motion comes into picture here. If the wing pushes the air downward, the air should also push the wing in the opposite direction with equal magnitude. This eventually results in the lift force, and the aircraft will be able to fly off the ground. Even today, the airplane make use of the same airfoil technology to fly, but with a high aerodynamically optimized airfoil shape. Thrust force makes an airplane move forward. To produce this thrust, a turbofan engine is used in modern civil aviation airplanes. Reaction force of high velocity exit jets gives the turbofan engine a thrust force. To produce this high velocity jet, the incoming air is passed through a compressor, combustion chamber, and turbine stages. The engine also drives the thrust force from the fan reaction. Thus, the turbofan engine produces a great amount of thrust and makes the airplane move forward. When the airplane moves forward, the relatively flowing air over the wings produces a lift force on the wings. Let's take a close look at the wing. You can note that the wing of a modern airplane is a collection of different parts. During takeoff, the flap and slat are extended downwards as shown. This increases the wing area and curvature of the airfoil. As the curvature increases, air will be deflected more. Thus, a greater lift force can be derived even at low airplane speed. As the airplane speed increases, the lift force rises. Finally, when the lift force is more than the gravitational force, the plane takes off. You can navigate the airplane the way you want with the help of three different wing attachments: aileron, elevator, and rudder. Pilots use them alone or together depending on the situation. Assuming you want to descend the plane, you can just lower the elevator. This will deflect the airflow as shown and will produce a lift. The lift force will create a moment that will make the nose of the plane go down. If you want to climb up, do the reverse. Now, let's assume the plane has to change its path. Just turn the rudder. Of course, turning the rudder will produce a lift force and make the airplane turn as shown. But such sudden change in flight direction may cause passengers discomfort. The professional way is the use of aileron. Just make one aileron go up and the other down. This will cause difference in lift forces and airplane will roll. Now, observe what happens. If the airplane still goes up, it is clear that the airplane has changed its path. All these movements of flap and other devices are controlled from the cockpit using a fly-by-wire system. You can see the different controllers pilot uses to navigate the plane. During landing, it is required to increase the drag. For this purpose, flap and slats are activated again because they have dragging capability too. The wing attachment called the spoiler is also activated to increase the drag further and reduce the lift. An interesting mechanism is used for lowering the flaps. The mechanism will rotate as well displace the flaps. We hope you enjoy the flight journey by exploring the science behind the airplane operation.
I build and fly aircraft. I've not been to any school. As a matter of fact, I do my research at home. I do just planes. I think planes. Yeah. Well, I went to primary school. Yeah. I went to secondary, and I was almost going to the university before this work really got intense, you know. And when I really studied our conventional school system here, I noticed that they teach you how to cram some of these principles and theory, you know, but it takes more than just knowing these principles and theory, you know, to bring something out. Some time in '92, I created an aircraft which took me about, I spent about 100 to 120 naira then, you know. It took me about 3 weeks to gather that money. You know, I built the aircraft and somehow I was nowhere close to actual flight, you know. So I tried again around '94. No way. You know, it was then I concluded that there is something spiritual about things that fly, you know. So I took a long break, you know. So, but somehow it was just like a destiny thing, you know. So I couldn't just give up completely. So the thing kept bothering me. Guy, even if this thing is spiritual, even if not witchcraft, somehow, maybe people get the witchcraft, you know. So I kind of mustered up courage, you know. Even if it is witchcraft, even if not bottle of water, I will go there and go and bring it out, even if it costs my life. You know, that was my resolution then, you know. So I put some effort again in 97. I created another aircraft, you know, but it didn't fly. But somehow I noticed some changes, you know, and which I now interpreted as, you know, guy, you need some more research. You know, so I took another break, like about 2 years. So I went into serious research, you know, a lot of reading, sourcing for materials on the web and all that. So around 99, I came up with another aircraft again. This time around, I was able to lift it off the ground, but the power source, the battery, you know, I was using a car battery, which required a long wire, you know. So I wish the aircraft couldn't carry from the ground. So it would just move to some point, leave the ground to the extent of the wire to just fall. So, and something funny really happened, you know. I wanted a means of carrying the battery along. So I went to rent a wheelbarrow, you know, put the battery on the wheelbarrow, and extended the wire. So somebody manning the wheelbarrow, then myself manning the plane. Guy, how far? You just said, yes, okay. Then I on the plane so that the wheelbarrow guy will be running alongside. You know, but something funny happened. The guy was just running along with the plane, but he wasn't washing his own part. He was washing the plane, and somehow he stumbled into this capstone, and the wheelbarrow somersaulted him. You know, it was funny though, but I was able to come up with something. So, but somehow I was able to lift it a couple of feet off the ground. That was when I said, that winch, when Oyibo shop, I don't shop am. There's an inbuilt battery here that needs to be charged. So that's what I'm doing now. I need to charge the inbuilt battery that will power the electronics here. You know. So while that is going on, I will need to fuel it. This engine uses a special fuel. Although it's a locally made fuel, I have to prepare that myself. See my filling station? You got it. So it's time to fuel. I don't have problem with fuel scarcity. See the aileron. All these are control surfaces. Yeah, this one is, you know, to direct the plane on the roll axis, you know, to stabilize the wings. You know, it's called the roll axis. Then you see the horizontal control surface on the tail. Yeah, it's called the elevator. It's used to control the plane on the pitch axis. That is, if you want it to climb or dive. Yeah, that's the elevator. Then you see another vertical one moving left, right there. It's called the rudder. You see that? It works like your normal steering in a car, yeah, to steer the aircraft left or right. Let me show you something about maneuverability. So sometimes I do attach cameras to my planes, you know, for surveillance purposes. Like I have the whole of this area, the shot of this area, you know, in my camera, you know, just taking the shot around, fly it low, slow, high, just to get shots. And I noticed that it can really make a good surveillance object.
Right from small picking, never reach 10 years, we start to dey do this thing. So we go out, we go pack all this can, we go cut them. We go kitchen side, we go do am. Now motor first start, it takes start am. So when they do am like that, e no go even create dey eat. So when Papa go see am like that, he go say, you no go comot your hand for this. You go flog am. I go even throw away those things wey they do before. We go think say you don't forget about am. Before we know again, you don't go pack them. You go kitchen side, you go carry fire, go cut the things, go do am. Not only the place, you know. My motor when I take the sell bread, I know they carry and go mechanic place. Anything wey wrong for inside, you know, even the one wey mechanic no go fit know, you go just detect am, you go do am. Almost how many years I never reach a mechanic place because he know about motor, and so he know about the plane, and so he still know about the motor.
The process from conception to final construction, the completion of a project is quite involved. And each step of that process must be done properly, or you could have problems. And one of the first things that my professor told me when I went to university was, as a structural engineer, you do not have a second chance to do it right. So you can only do it right once. I'll quickly describe the process to you just so you understand the things that can go wrong. It starts with the design process, where the owner has decided to build something based on the agreed master plan. It goes to an architect. Architect designs the building, creates the form to fit the function of the building. And then he brings in his consultants, structural engineers, electrical engineers, mechanical engineers, landscape, and so on and so forth. We, the structural engineers, make sure that the building is able to withstand all of the loads that is expected to carry, gravity loads and lateral loads from wind and earthquake or what have you. Now, the way we perform function is this: we perform calculations, detailed structural calculations, and those calculations are transferred to drawings. So we draw exactly what we want, we specify what we want. The drawings and calculations that are supposed to go to the municipality, who is supposed to review what we have done. Oh, by the way, those drawings and calculations should be performed by someone who is very experienced, either by training, school, and practical experience. So the municipality reviews these drawings. If the reviewer agrees what we've done, they will approve it. If not, they will send comments back. So after this process is completed, then it goes to construction. Now, in the construction process, the contractors must use what we specified. They must build this strictly in accordance with those drawings. They cannot deviate from what we specified without getting the blessing of the structural engineer. But what you have going on now is sometimes people may add additional floor to a building that's already been designed and approved. You cannot do that because there's so many elements that can go wrong. For instance, the columns, that's what you call pillars, are meant to support a certain amount of wood. If you add two more, a floor or additional floors on it, you can overload those things. And when a column fails, that's disastrous. It can be very catastrophic. Also, the foundation is designed to carry a certain amount of load, so you cannot keep adding things beyond what a structural engineer has calculated. In other words, you have a building that's designed for something, then you want to reuse it for something else. What a structural engineer would do is, one, look at the drawings of the building. You can work backwards to see what those elements were designed for. Failing that, or quite frankly, in addition to that, you would actually do an assessment. You go to the building, assess the building. For instance, in more advanced societies, if you have, say, a foundation, let's take a very simple foundation, what they call a spread footing, it's square, it's concrete pad with reinforcing steel in it. If you don't have the drawings, there are non-destructive ways we can determine what the reinforcing steel is inside those footings. We can measure them. We can actually do non-destructive testing to see what the strength of the concrete is. So knowing this and armed with this information, and of course information pertaining to other elements of the building like the beams, the slabs, the columns, and what have you, armed with this, I can now say, okay, to the architect, what do you want to do? How do you want to retrofit or change this building? It tells me, then I start doing calculations. And my calculations will tell me if the elements that are there are sufficient for the additional loads. If they're not, I can design reinforcement to elements that need it. I described the process. A lot of things can go wrong, and it can happen at any one of those steps. In the design process, if the engineer makes a fatal error that no one catches. For example, if you say 2 + 2, makes a mistake and calls it 16. And he bases his specifications or drawings on this wrong number. That's an error. If no one catches it through the process, it could get translated into a building construction. It could result in a catastrophe. Now, the second process, where I talked about the drawings being reviewed by the municipality, is really meant to catch such errors. The third part of this process, which is construction, is really where a lot of the mistakes can be made. Let's take, for instance, concrete. Concrete is a composite material. Concrete is made of cement, water, sand, and I call it sand. It's called fine aggregate, or gravel, or coarse aggregate. Each of those 4 components is really essential for making good concrete. I'll give you an example. Cement in of itself, if you add water to it, it's a process called hydration. That's how cement becomes paste that binds all the aggregates to mix the mass. That's concrete. The strength of concrete depends on how much water you add in the concrete. I'll give you an analogy. If you add too much water, that means water don't pass Gary. If you don't add enough water, Gary don't pass water. So you have to have the right amount of water in the cement or in the concrete mix for hydration to be complete. If you have too much, once you pass that point, if you add too much, the strength of the concrete starts to take a nosedive. So during construction, those things should be monitored. There should be tests conducted on the material before they're installed. There should be somebody who's qualified watching those things. So in, like I say, more advanced societies, these things are really carefully taken care of during construction. Because if you ignore it, anything can go wrong. You can clearly see the columns, and you can see the reinforcing steel sticking up. If you look closely, there are ties that's used to hold those vertical bars, right? There's a quick thing on columns. When you load a column, part of the load goes into the concrete itself. The other part of it goes into those reinforcing bars. It's very elementary description. If you think of a reinforcing steel bar, if it's very skinny, it's a very tiny bar. If you load it, right, what do you think will happen to it? It will buckle. So those ties that we put on it, those things that hold it together, it's meant to keep the length of it short enough such that it can carry that load. But if the contractor decides, if the engineer says, look, space these things at 12 inches apart, and the contractor, because he wants to save money, spaces at 6 inches apart, he's defeated the purpose. So that something as simple as that could lead to a collapse. Something as simple as having too much water in your concrete mix can lead to collapse. Something as simple as not placing the reinforcing steel where the structural engineer says to place it can lead to collapse. In some cases, the structural engineer visits the site to monitor the construction, but it's really not his job to do a continuous inspection. So I believe that we should have in this country a requirement, particularly for very sensitive buildings, where there has to be a qualified testing agency on site to monitor the placement of the reinforcing steel, to monitor the concrete mix, and how it's produced and how it's placed, and how it's compacted, even how you cure the concrete matters.
I hope you enjoyed the program. For inquiries and sponsorship, call these numbers. Join us for another informative and interesting edition next time. Bye.